Alright, time for another draftphysics.com, debatephysics.com also, but they won't debate. So, Veritasium. I have done a few Veritasium videos. I came up with the only correct answer to why you can build a car that can go faster than the wind pushing it, so I got that one right. I did his double slit fake experiment where, he demonstrates that it's the photons, create the pattern. Let's see, what was the special? Oh yeah, with single photons, and but they don't understand what a photon is. So they don't even know what a single photon would even be. And obviously, I pointed out the obvious that he took an experiment you're supposed to do over 40 days, or at least 40 hours, and turned it into one you do in 5 minutes because it didn't work when he tried to do it the right way. It's that simple. It didn't work. All right. Jeez, so he had to cheat. And he did it right in front of everybody and nobody cared. But I mean, it's just a huge, giant cheat. You can't claim single photons if you're sending trillions of them in 5 minutes. Yeah, no, not going to work. Anyway, not going to work for reasonable people. Anyway, entropy is the subject of this other crappy video, and it's whatever, 14 million views, and it's crap science. And the funny thing is the references, because it's basically a bunch of other people. But so he says, a huge thank you to those who helped us understand different aspects of this complicated topic. What's frickin' complicated? So this whole entropy thing is so silly, right? Because a magnifying glass breaks entropy. And clearly gravity is doing the exact opposite of diverging things. It's compressing things. It's consolidating things. So if you think of entropy as the fact that energy can be dissipated, well, it can also be concentrated. And again, something as simple as a magnifying glass proves that. So there's nothing special about the one way. The divergence of energy is not special. The convergence of it is exactly the same thing, and that's what gravity does all the time. It's converging things. And so it's silly to say there's more divergence than there is convergence. They have no evidence to support such a theory. And it's also silly to say we can't capitalize on either side, that we can't take an advantage of an explosion where everything's diverging, and we can also take advantage of the fact that the Earth is gravity, and we can catch raindrops as they're compressing the Earth and steal their energy. So I mean, this is just the silliest subject. It's just junk science all over the place. I'm just amazed. All right, so it says Dr. Ashmeet Singh. Let's see if I can read some of these names. All these people who help them misunderstand. Suprina Kakabababla, Dr. Hus Chajosisoshian. I mean, fuck, I can't even read their names. Baijo, Dr. Baijo Batra, Dr. This is Timon Idemia, Avradio. I mean, nobody's named Bill. It's just amazing. They must have a real bigotry against Bills and Johns and Jeffs or something. Not a single good old American name. Not a single one. Even Albert Einstein. Albert would be a good name. Musha Tavavoyoy. So all those people helped write the script for this pile of shit. Okay, I mean, sorry. But it's a piece of garbage. Okay, and well, those are the people who consulted. So those are the consultants. And then he has a staff of writers. Now, all of these links are all to all these other crappy videos. So this one's actually one I already did. This was the chaos video by that Al-Kahari guy. So one of his videos in here somewhere. Yeah, Spark. So the true power of atoms, order and disorder. I think that's really that's his entropy video. that I pointed out was crap. So Steve Mould did a video on it, so I'll have to go watch some of these other pieces of garbage. Wikipedia, forget about it. Anyway, this is just the silliest. I don't even know why. Why do physicists do this? Pretend there's a subject here when there's no subject. You know, it's just, all right. Well, anyway, let's get to it. So, a special thanks to the patrons. So, it was written by Christopher Membelis, Derek, the guy who does the videos, Veritasium, and Petra Lebevev. So, and there's editors and animators and molecular additional videos, Fight Lab, National Center for Superconducting Applications. I wonder what their contribution. Oh, and music, of course. Oh, brother. I mean, this isn't science. This is just silly frickin' pop culture drivel dravel. Yeah. Ugh, just so bad. Alright, anyway. So we're going to play for this part where he's going to do this example of Carnot, who everybody makes out to be this great inventor of some great thing. And he didn't invent nothing. It's just, you know, I'm not saying he wasn't. I'm not saying he didn't say some good things about understanding the nature of heat. Maybe even said heat's momentum. He might have said that. I don't know. I mean, obviously is. And clearly, if you're going to say you're conserving energy here, you can't make motion over there. It can't be in both places. So there's no such thing as this perfect heat engine they're going to describe here. So his idea of a perfect heat engine really can't work. That's why no one's ever made one, is because it really can't work. It's not even that you have losses to the environment, because we could understand those and we could compensate for them and still show the principle. But the principle doesn't work.
Heat engines. And one of his key insights involves how an ideal heat engine would work. One with no...
I guess I should check volumes here. It's so difficult. I have to always figure out what, I gotta lower this and increase that and blah blah blah, and it's sort of annoying. You gotta figure all this out. But anyway, it's not your problem, but I do wish to get the sound of videos I play better, so I really should pay some attention to it. Sorry for the interruption.
Friction and no losses to the environment. It looks something like this. Take two really big metal bars, one hot and one cold. The engine consists of a chamber filled with air, where heat can only flow in or out through the bottom.
So I don't even know why he would say flow in and out. You'd have to have some sort of really good conductor of the heat. So the idea of flowing in and out doesn't make any sense because they can't let the air out. So he's sort of implying that there's an opening. There's no opening.
Inside the chamber is a piston, which is connected to a flywheel. The air starts at a temperature...
So it'd be probably better if this animation kept you, if they did it sideways, so you'd get the idea that it's connected to a flywheel.
Just below that of the hot bar. So first the hot bar is brought into contact with the chamber.
So obviously it's not hot now. So the gas is not hot. And now they're going to heat it. All right, now, so if you thought of it as just being air pressure, that's how I better understood it. Was if I said, okay, if I put 10 pounds of air pressure in, what's the piston going to do? Well, it's going to go up a certain level and stop. It's not going to give any momentum. And if I go 30 pounds, so yeah, okay, go a certain height, but it's not going to go any higher than that. The flywheel's not going to keep going. It's not creating enough velocity to have momentum. And if it did, it would start making the stuff colder because it would be expanding the gas and it would be pulling back the other way. So it can't go much faster. It can't gain much momentum is the idea. So if I went to, say, 100 pounds, push the piston right up to the top, where the piston would stop. And so the wheel would stop. It won't have any momentum. It can't have any momentum because I haven't put enough velocity into the piston. for the wheel to have momentum, I have to put a high velocity into the piston. So I have to have a much higher pressure. So the pressure has to be more like it would push the piston much further. So like 100 times further than I'm going to allow the piston to go. So that's a key thing to understand, is you have to push the piston faster than just the 30 pounds of pressure or 20 pounds, or this slow rising heat thing won't give the wheel any momentum at all. So it's not going to turn and have energy on the down cycle. There's no down cycle because you never had an up cycle. You never moved the flywheel fast enough to do any work at all.
The air inside expands with heat flowing into it to maintain its temperature. This pushes the piston up.
So energy, okay, something real, is now flowing from one thing and going into the other. So the hot bar is getting colder. They should show that. They should show it getting colder as this gets warmer. So you should start with a red hot bar, right? Can you see this? Yeah, you can see most of it. They should, maybe I should do the pop out screen thing. All right, let me pause and do that. Well, I don't know if that was that helpful. So anyway, let's continue.
Turning the flywheel. Next, the hot bar is removed, but the air in the chamber continues to...
So it doesn't. So the air in the chamber doesn't continue anywhere. You're not adding more heat. It can't continue anywhere, but you're not going to add any more pressure. So unless you added a whole bunch, like it got really hot very fast, okay, so you have to add more pressure than you're actually at the position of that. So it has to have enough reserve heat in it that it would keep going. It can't keep going unless you have more heat in there than the place it's at. So it has to keep pushing because there's more heat in it. But there really isn't. So it's just not true that it's going to keep expanding. It's not going to keep expanding unless you have an explosive or some other thing where you create a tremendous high pressure. This pressure is just going to be gradual. So there's no way it's going to create any momentum, and it's no way 1,000 times warmer than the height of the piston. And that's what you need to do. You need to put so much energy in that you move the piston very quickly. All right. So it's just wrong that it's getting hotter as it's expanding. It can't get any hotter. It has all the heat it's going to get. It's not going to expand anymore because you already expanded it with the heat you put in. The heat expanded it as soon as it had contact with it. It started expanding, and it's not going to expand more once you pull the heat away. That's the end of its expansion.
To expand, except now without...
So it's not going to continue, and the only way it could continue is if you gave it a very high velocity, and then the flywheel overshoots, and then you're going to be expanding the gas and it'll start cooling, and then you're going to be going the opposite way.
Heat entering, the temperature decreases. In the ideal...
Okay, so none of that can happen because you had to have more pressure. To get any velocity, you had to have much higher pressure. So you're not going to get cold, you're just going to get less hot. All right, so it's not going to do this instant transition from I was terribly hot and now I'm just going to get cold for no good reason. That's not going to happen. So what you really have now at the peak point, what you really now have is a hot gas still in the cylinder. It didn't lose that much of its heat, okay, because it's pushing the cylinder. So this is an idealization. So it's not losing heat to surfaces or any of this other stuff. So all you've got is a gas now that's hotter than the gas you started with, okay, a lot hotter.
Case until it is the temperature of the cold bar.
So now it is in no way can be the temperature of the cold bar. So it's just not going to happen. All right, it doesn't have enough momentum for that to happen. So they're almost implying that you gave it enough pressure to go halfway with the heat, and then it started expanding the gas and cooling it by expanding it, and that would stop the wheel from turning. That would be doing work. So for it to cool the gas, it would have to do work against it. It would have to be pulling on those molecules, stretching them. That's going to be work. You have to apply a pressure to expand the gas. So it's not going to give you motion in your flywheel. It's going to do exactly the opposite. It's going to stop your flywheel and even reverse your flywheel eventually. But obviously it's never going to happen. It's not going to just instantly get cold.
The cold.
And he says right a temperature right below the cold, right above the cold bar. Well, then this wouldn't work at all, because if you're only a tiny amount of temperature above, there's not going to be enough differential in the temperature for you to do anything. This isn't going to expand at all. You're saying, look, there's 10 pounds of pressure in here. I'm going to make it 10.2. That's not going to expand your gas. That's not going to move the piston. It's not going to do anything.
Bar is brought into contact with the chamber, and the flywheel pushes the piston down.
So the flywheel pushes the piston down. That means it has to have momentum. How did it get the momentum? You in no way ever pushed it fast enough to give it enough velocity to have its own piece of the energy in terms of momentum. So unless you explain how you had enough pressure to move the cylinder fast enough to give the flywheel momentum, you're out of luck. You're not going to have anywhere near enough energy to compress the gas, especially since the gas isn't cold. It's still hot, hotter than what you started with, and now you're compressing it and you're going to make it hotter. So now it's going to be a lot hotter.
And as the air is compressed, heat is transferred into the cold bar.
So that's the only part that's a little bit accurate, is that yes, once you start compressing, you're going to have to start getting rid of the heat somewhere, because you're not going to be able to heat it because it's so much hot. It's going to be hotter than your hot bar. And so the concession is right here. He says, well, now you take it away just when it's a tiny degree higher than the hot bar. I mean, a tiny degree colder than the hot bar. Well, what good is that going to do you?
The cold bar is removed, the flywheel compresses the gas further, increasing it.
So again, it keeps saying the flywheel compresses the gas further. It can't do that unless you gave it enough momentum, and you clearly didn't. Because if you did, you'd be stuck with a very, very hot gas in here now. Very hot. Much hotter because you never got rid of the heat.
Its temperature until it is just below that of the hot bar.
Just below. What's just below? What kind of work can you do with a differential that's just below? You're going to do enough work to give the flywheel momentum? No chance. You're not going to do enough work to even move the cylinder 2 millimeters, and it'll stop.
Then the hot bar is connected again, and the cycle repeats.
So again, the hot bar is only a tiny bit warmer than the gas in there. How does something that's only a tiny bit warmer make the gas expand like that? No, there's no chance. So this isn't a heat. This is not. This isn't a useful diagram of how physics works, how heat moves.
Through this process, heat from the hot bar is converted into the energy of the flywheel.
So we know the whole time the cold bar is getting hotter and the hot bar is getting colder. And now he's going to pretend that somehow we can just reverse it and put the hot back in the hot bar and the cold back in the cold bar, which you're not going to do.
Flywheel. And what's
so
interesting
just
to
understand,
note about Carnot's ideal...
If you knew this worked, right? If you thought about this actually doing work, okay, so the flywheel's spinning and there's a bar moving on it and it's doing work somewhere, lifting a horse or something. You know the energy can't be in both places. You can't have some perfect perpetual motion energy machine and do work over here. You can't. Even if you had your perfect machine and you're conserving your energy, you can't do work anywhere in any other location. You can't have a spinning wheel and a conserved heat transfer.
Engine is that it is completely reversible. If you ran the engine in reverse, first the air expands, lowering...
So I don't know. So the air just magically expands. So the hot bar was there, and now the air is expanding, and it's still expanding. So it's almost like they're saying it's some explosion. There's no explosions here. They're just, you put some heat in, the heat creates pressure. It takes maybe a little bit of time for the pressure to push the cylinder, but it's clearly going to decline in pressure as the cylinder moves. So as soon as the cylinder moves, if I have 30 pounds of gas, I put in there, then the cylinder moves and all of a sudden I got no pressure because the cylinder is going to expand to the pressure I put in. And once it expands to the pressure I put in, that's all I got. It's not going to keep going. 50 degrees or 60 degrees is basically just a level that the frickin' piston's going to rise, and you have to have a lot higher temperature if you're going to move the cylinder fast enough to spin a flywheel.
The temperature, then the chamber is brought into contact with the cold bar, the air expands more.
So again, it expands more is just not even connected to his own video. The air expands more. That means it's getting colder, okay? But why is it doing that? The wheel's not doing work to make it get colder? Well, of course it has to be doing work. Well, where did it get the energy to do the work? Because your expansion cycle wasn't fast enough to do work on the down cycle. You clearly haven't given your wheel enough momentum to do the hard work of pulling on the vacuum. I mean, it's essentially a vacuum, and you're pulling on the vacuum, and you're going to force the air to fill a bigger space. That's work. It's work to expand the water molecules or the air molecules. It's work.
Drawing in heat from the cold bar. Next, the air is compressed, increasing its temperature. The chamber is placed on top of the hot bar, and the energy of the flywheel is used to return the heat back.
Right, and that heat, though, has to be hotter than the hot bar. And the question is, if you didn't have enough momentum in the first cycle to even get to the peak of the cycle, how are you going to have enough energy though? How is the flywheel going to have enough momentum to compress the gas hotter than what you started with? Hotter than the hot bar. There's just no chance.
Into the hot bar. However many cycles were run in the forward direction, you could run the same number in reverse, and at the end, everything would return to its original state.
So that's just not possible, because what in fact you have done is give a bunch of parts momentum, and it's just a fact that you did that. There's stuff moving somewhere else. You can't have stuff moving somewhere else and say, I have the energy here in the battery still. You can't you can't conserve the battery and do motion
with no additional input of energy required. So by running an ideal engine, nothing really changes. You can always undo what you did.
So again, it's this idea of an ideal engine that does zero work. Okay, so as I understand, it can't do any physical work. So all it can do is spin the wheel, but technically spinning the wheel is work in our real world. Now, maybe in space with perfect bearings, spinning the wheel isn't enough to worry about. I mean, I don't know exactly how to calculate that, but it's still energy not in the battery. So if the wheel is still spinning, then your system is missing the energy it takes to spin the wheel. And if you did any work in some other location, or you moved some air, you did whatever you did with your spinning wheel, if you did any work with it, obviously that energy is missing.
So what is the efficiency of this engine? Since it's fully reversible, you might expect the efficiency to be 100%. But that is not the case. Each cycle, the energy of the flywheel increases by the amount of heat flowing into the chamber from the hot bar, minus the heat flowing out of the chamber at the cold bar. So to calculate the efficiency, we divide this energy by the heat input from the hot bar. Now the heat in on the hot side is equal to the work done by the gas on the piston, and this will always be greater than the work done by the piston on the gas on the cold side.
So he's saying that work is greater. Now, there's no evidence that it's greater. There's just the fact that you're never going you never move the piston because you didn't put enough pressure in to move it fast enough for it to have momentum so it could do work. The flywheel never had enough momentum to do any work on the down cycle. It has no pushing power.
Which equals the heat out. And this is because on the hot side, the hot gas exerts a greater pressure on the piston than that same gas when cold.
Obviously, he's saying that, but that's not true. And the real point is you have to make the gas much harder than the pressure of the peak height. You have to move this thing, you have to put more pressure in than you need, to give it momentum. To move the flywheel to this position, well, that's one thing. I can move it, and it stops. To have it go further, that is to give the flywheel actual momentum, you have to increase the velocity of the piston. So you have to put more energy in than it takes to get to the height you're pushing the piston, because you have to start increasing its velocity.
To increase the efficiency of the engine, you could increase the temperature of the hot side, or decrease the temperature of the cold side, or both. Lord Kelvin learns of Carnot's ideal heat.
So this is really a really not obscure point, kind of abstract. That somehow you could only have a perfect engine if you had a perfectly cold thing. You can't really have an infinitely hot thing, so let's just go with the thing that's more realistic. And still it's not going to change anything. There's no difference between the two cycles, theoretically. There's just no difference. It's a gravity thing. What goes up comes back down with the same energy you threw it up with. So if your flywheel is ideally frictionless, you're not going to lose any energy. But you never gave the flywheel any energy is the whole point. You never gave it enough momentum to do any work.
The engine and realizes it could form the basis for an absolute temperature scale. Imagine that the gas is allowed to expand an extreme amount, so much that it cools to the point where all the gas particles effectively stop moving.
So again, that wouldn't happen, right? I mean, you could give it velocity and it will overshoot like a spring. Okay, so you give it a high velocity with heat. The momentum of the piston, let's just say, keeps going. All right, and what's it going to do? It's going to expand the gas, cool it, and stop because of the expansion. All right, so that can happen, but again, it's just a spring. Then the cycle isn't going. The cycle won't continue if you try to pull any energy out of it.
Then they would exert no pressure on the piston, and it would take no work to compress it on the cold side. So
I don't know, no pressure to, no energy to compress it. You get it? No, it's not going to be an issue compressing it because you've already expanded it. You've made it cold. The color is blue. You've made it cold. It's now contracting. It's pulling the piston down. The piston doesn't have to do any work. The gas itself is now cold and it's in expanded form, so therefore it's more expanded than it wants to be, so it's going to contract.
Heat would be lost.
I mean, that's what they did that was the innovation with steam engines, was the condenser. The condenser was the huge innovation that, made the thing so much more efficient, was just the fact that you cooled the cylinder and cooled the gas connected to the cylinder, and therefore made it much easier to get the gas out of the cylinder, to get the cold steam out of the cylinder.
This is the idea of absolute zero, and it would make for a 100% efficient engine. Using this absolute temperature scale, the Kelvin scale...
So again, it's not really an engine, and I would argue that it's not 100% efficient if the thing is moving. So it's not 100% efficient when the thing is moving because you have energy in the thing moving. And it can't be in the battery, and in the moving thing. Can't be in both places. So whatever your source of motion is, the power you're using to move something, you have to lose some power out of it for you to have something over here moving. So it can never be perfectly efficient.
We can replace the amount of heat in and out with the temperature of the hot and cold side respectively, because they are directly proportional. So we can express efficiency like this, which we can rewrite like this. What we have learned is that the efficiency of an ideal heat engine doesn't depend on the materials or the design of the engine, but fundamentally on the temperatures of the hot and cold sides. To reach 100% efficiency, you'd need infinite temperature on the hot side or absolute zero on the cold side, both of which are impossible.
Right, so you don't need either one. You're never going to get perfect efficiency, so I don't even know why you would talk about it. You're just talking about getting to better efficiency. And it seems kind of obvious to have to say something like that. Obviously the perfect efficiency is always going to be very difficult, because at the peak of the pressure cycle, right, the explosion happens inside the engine. You have a bunch of hot gas still in the cylinder, right? The cylinder did this expanding. It wants to expand more, but the cylinder wall is saying you can't expand anymore. All right, and you're at the end of the cycle, and you're stuck with a bunch of hot gas. Well, what do engines do? Well, they just spit it out. Okay, and that's why they have exhaust pipes. It's because, there's no way to use heat fast. Okay, to change energy from diverse, little pieces into something not in little pieces usually takes time. Like a magnifying glass does it really quick, so it's no problem. But I'm just saying it's a little harder to take heat stuck inside of a material and get it to move quickly out through some conduit. And that's the limitation. So yeah, the engine heat can't be used because it takes a lot of time to organize the diverse heat and get it to move in one direction.
In practice. So even with no friction or losses to the environment, it's impossible to make a heat engine 100% efficient. And that's because to return the piston to its original position, you need to dump heat into the cold bar. So not all the energy stays in the flywheel.
Well, you're obviously dumping it in the cold bar, and you're also losing it on the hot side. So again, you keep pretending you don't have to lose any on the hot side. Of course you do. So both of them, to do work, you have to lose heat, okay? You have to lose energy out of the system. So no matter how you make it, you're still stuck. If you're going to move something else, the something else will consume energy. We'll use it.
Now,
we'll keep it occupied. And again, you can put it back in, but I'm just saying if you have anything still moving, okay, you didn't conserve it. And if that moving thing did any work in the world, that is, it left any energy behind, obviously you're not going to conserve it 100%. But again, this whole conversation shouldn't be about, making a perpetual motion heat engine. It should be about how you can gain huge efficiencies by getting rid of heat you can't do anything with.
Carnot's time, high-pressure steam engines could only reach temperatures up to 160 degrees Celsius, so their theoretical maximum efficiency was 32%, but their real efficiency was more like 3%.
So the catch is that obviously high pressure is always dangerous, but steam expands with every degree you add. There's this huge expansion thing, so it expands not quadratically, but by some increase, okay, based on temperature. So the higher the temperature, the more expansion you'll get out of the steam. And it's like this 20 times kind of thing or something. It's a pretty good expansion. Steam can, I heard a boiler guy say it, steam can kill people if you can release enough of it. So if there's like a big burner, a steam thing for a big building or something, the steam can basically displace all the oxygen and air in the room, and you can suffocate because the steam just takes away all the breathables.
That's because real engines experience friction, dissipate heat to the environment, and they don't transfer heat at constant temperatures. So for just as much heat going in, less.
So we know that, look, I mean, all these things, all these engines really aren't about the heat. They're about the expansion, the expansion of a substance. And obviously the better engines work with something that is expanding. So, air would not be very practical, so that's why they used water and steam, because the steam is so much bigger than the water. 100 times more space it occupies.
Energy ends up in the flywheel. The rest is spread out over the walls of the cylinder, the axle of the flywheel, and is radiated out into the environment. When energy spreads...
So the key point I'm making is that the flywheel, to have momentum, enough momentum to do work on the down cycle, it means you had to give it more velocity than just moving the piston like this. You had to give it enough velocity where the flywheel itself, the momentum caught up in it, does the work on the down cycle. It can't do any work if all you did was turn it and it stops at the top. It has to have reason to keep going. So you had to add more velocity.
Out like this, it is impossible to get it back. So this process is irreversible.
So there's no irreversible process, so that's more nonsense. And it's clearly in the universe, so they're going to apply this to the whole universe. And the whole universe is a huge demonstration of exactly how you do it both ways. So like I said, gravity is this huge force in the universe. It's made, it keeps galaxies together, it holds all this stuff together, it makes suns, makes Earths, makes Pluto, makes Saturn. And all of those things are a consolidation of energy. They're all a consolidation of momentum. All kinds of things with momentum colliding into the Earth. And right now you're being pushed with momentum, real momentum. 1 mile an hour of momentum every second. It's the truth. Okay, if I push you 1 mile an hour into a scale, you'll weigh your mass. Okay, you'll be able to weigh your weight on the spring. All right, so it's momentum, it's real motion, and you've converted it. You've put it all into a tiny little place. You're compressing it into a little space. You're doing exactly the opposite of entropy, in the sense of you're creating very low entropy. Now he's going to go on to say things in this video that are just crazy, like black holes have a lot of entropy, when no, they are very absent entropy. There's zero entropy. They're gigantic stores of potential entropy. The whole word is stupid, because they're calling entropy the spreading out of energy, but there's no word for the consolidation of energy. So you have this word for spreading out, but you don't have a word for unentropy. Am I supposed to say unentropy? Black holes, suns, Earths, Plutos, all this stuff is low, is full of unentropy, anti-entropy. Yeah.
The total amount of energy didn't change, but it became less usable.
So this word usable is very, human-centric, doesn't really have anything to do with reality. The universe uses it. Every bit of radiation in the universe is being used, and I would make a simple argument to you that it all adds up to gravity in the end. So the microcosmic microwave background radiation, it's all coming from all directions on the Earth, hitting it. Well, what does that equal? A consolidation, right? There's no other way to look at it. The pressure's on the outside, it pushes it to the inside in every single surface on the Earth. So right now we're being compressed, we're being made unentropic, okay, by the microcosmic microwave background radiation. So there's no other way to look at it. It's all the energy is just going to end up where it expands one place, it's compressing in another place. It's just as easy to compress in this universe as it is to expand. Making a sun and blowing a sun up are the same action. There's no difference. Or slowly burning a sun. Oh, I don't know why. Well, I can pause. All right, leave us continue.
Energy is most usable when it is concentrated, and less usable when it's spread out.
All right, so that's a statement. I'm just saying it's not true, okay? Because sunlight is very spread out by the atmosphere, and it makes it incredibly useful to us in a sense because it's coming from all directions. If we didn't have an atmosphere, then the sunlight would be, brutal, frankly, and we'd have to have shielding to keep us out of the 400-degree heat. So it's so let's see what's a way to put this. Again, the magnifying glass is as good as it gets in terms of a simple enough diagram that all you need is a simple device. And you've solved the problem of fixing entropy. Play.
Decades later, German physicist Rudolf Clausius studies Carnot's engine, and he comes up with a way to measure how spread out the energy is. He calls this quantity entropy.
Right, so it doesn't mean anything. It's just, this isn't even real math. This is just fake notion. I mean, it's just a fake concept, a fake thing, some kind of ambiguous amount of spreading. Any spreading is spreading, so any spreading is going to be counted as spreading. So it doesn't even matter how tiny the diversification is, or the spreading. It's a useless concept. This isn't a real thing. This isn't a real quantity.
When all the energy is concentrated in the hotbar, that is low entropy. But as the energy spreads to the surroundings, the walls of the chamber and the axle, well, entropy increases.
Look, the center of the Earth is molten, okay? The reason is because it's storing energy. There's a ton of pressure there. It's a bunch of stored energy. It's a battery, essentially. And yeah, it just runs hot, okay? So, but that's what it is. There's a bunch of stuff pushing from all sides. But you don't call that entropy. You call that exactly the opposite. You call that unentropy.
This means the same amount of energy is present, but in this more dispersed form, it is less available to do work.
So again, it's less available to do work. The rain is very available. The rivers, the streams, it's all very available. So not a problem. We store water in a water tank, right? So we put it in a low entropy state so we can take advantage of it. But in a sense, okay, what we do is we expand it, we give it back to entropy. But the fact is when it finally gets used, its eventual task will be putting weight on the Earth, creating less entropy again. So it's really a cycle started by less entropy. Gravity's doing it, and gravity is making unentropy. A lot of unentropy.
Work. In 1865, Clausius summarizes the first two laws of thermodynamics.
So crap, they're just crap. So these are just look, the fact that high pressure goes to low pressure, or heat goes from hot to cold, that is almost too stupid to have to make a law out of.
Like this. First, the energy of the universe is constant.
All right, well that's fine, yes, right? But that's just another restatement of Newton's laws in a way. But yes, of course. So if they really believe this, right? But the word energy here is the big catch, right? Because what do you mean by energy? mv squared? Yeah, that's not real. So what is energy? Energy is just momentum. It's matter moving is energy, and force moving is energy. So if there's a piece of force flying by, a cell phone call or something, some photon, that's a hunk of energy. And then if I, flick something in your direction, that's energy. If I poke the camera, that's energy transfer. And all of those transfers all add up to something that just recognize it's like a substance, and there's a certain amount of the substance, and if it was a color or if it was some kind of thing we could see, we could just watch it transfer. Well, they actually do that. That was in the Al-Kahari video. He touches something hot, and then he touches his shirt, and he just moves the heat around. Yeah, well, that's all there is. There's moving momentum. The heat is momentum. It's motion. Atoms moving is momentum. I shouldn't have to explain that to physicists. Fuck. They have a doctorate in physics, and I have to explain that if atoms are moving, they have something called momentum.
Second, the entropy of the universe tends to a maximum.
Alright, so that's the crap, okay? Obviously, the universe is tending to fucking make burning clumps. I mean, he's got a picture of the burning universe in the background, right? So there's a bunch of pictures of burning stars in the background. They're all going to just burn out? Is that what the universe does? They just made a bunch of stars, and then they'll all run out of stuff, and then they'll all just burn out, and it's never going to make another one. No, it's always, the matter is also conserved. If there's something blows up and little pieces go flying around, guess what? They're going to go somewhere and stick to something. Therefore, they're going to put their entropy back into unentropy. I mean, this is really, it just makes you wonder about physics. And, the fact that they haven't got the energy thing right at all, and then to screw up something as simple as conservation. Okay, it's really not that complicated. If you make something move over there, you have to use what you had over here. It's money, okay? You give away $5, you lose $5. They gain it, you lost it.
In other words, energy spreads out over time.
All right, so it doesn't, and you have no reason to believe it does that, and it's just crap. I mean, you could, theoretically, we could all sit here and say, okay, look at the universe and just say, okay, the photons themselves, where do they go? The ones that don't hit anything, right? So I make a photon, poof, and it just happens to fly in a direction where there isn't anything. Now, I don't even know if there is such a direction, right? I mean, the Hubble kind of is indicating there's something everywhere. So almost doesn't matter where I shoot the photon, it's never going to get very far because it's going to hit something. But let's just say it doesn't hit anything. Well, then what happens? Obviously, the universe got colder because I lost a piece of energy. So I would argue that probably the universe is a bubble, and it just bounces off the outside and comes back as the microwave background radiation.
The second law is core to so many phenomena in the world. It's why hot things cool down.
So again, it just isn't true. Things. The spreading of energy is just like a bullet can be sitting on the shelf for 50 years. Okay, it doesn't and you decide when to allow it to do its entropy thing. Okay. And, and we stored all this oil, millions of years, 300, 400 million years. Okay, the stuff has been sitting in the ground, just being unentropic. So it's just wrong to say the cycle doesn't go both ways just as easily.
And cool things heat up. Why gas expands to fill a container. Why you can't have a perpetual motion machine, because the amount of usable energy in a closed system is always decreasing.
So it is, and it is, and it is, and it's just wrong, blah, 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 blah. The energy is not decreasing because there's always some mechanism somewhere where it's going to collect it again. It's going to put it back in a battery somewhere. There's lots of batteries, okay, and eventually the energy is going to hit something, and when it hits something, it's going to make it less and have less entropy. Yeah, that's what it's going to do.
I am proud to have Tim.
Oh, brother. Yeah. Nobody and nobodyer. Who are these people? Well, why are they going to run anything? Oh, fuck. It's just so sad. It's a pathetic world we live in. Pathetic. Science is shit. Politics is shit. Just shit everywhere. Alright, he says the most common way
to describe entropy is as disorder, which makes sense because it is associated with things.
So it's not disorder, it's spreading, and that's all it is. Okay, you put the energy in little things, and it's hard to organize little things. You could argue when something has motion, it has heat in one direction. So all you're saying is I took a bunch of fish swimming in all kinds of directions, and I just bent them all to swim in one direction. And that's all there is. So there's the herding cats kind of argument. Yeah, it's a little bit of trouble to herd cats, but we can actually do it, right? We can take a pen and we can make one door, and we can make all the cats go out the one door, like a rocket engine. We can figure out ways to take advantage.
Things becoming more mixed, random, and less ordered. But I think the best way to think about entropy is as the tendency of energy to spread out. So why does...
So, yeah, and you know, spread out to what? Again, it's all you're really saying, though, is you're going to consolidate it, or you're going to... so there's probably better words, like a density argument. You're going to make the energy more dense, or it's going to be less dense. And it's a little more trouble to figure out a way to make the less dense than it is to figure out how to blow something up. I mean, breaking things is easier than making things. But it's just a human equation, really. The universe doesn't have any trouble making things.
Does energy spread out over time? I mean, most of the laws of physics work exactly the same way, forwards or...
So that's another one of their stories they tell that isn't entirely true. So that other guy... Phoenix something or other, Alpha Phoenix or whatever the hell, he made some argument like that about something. He just ran the film in reverse. And the truth is it won't happen in reverse, because the reverse has things getting faster, you know, because of friction. Things that were slowing down ends up speeding up. And that ain't going to happen. It ain't going to magically speed up.
Backwards in time. So how does this clear time dependence...
I mean, things like friction you can't run in reverse. There's no way to run friction in reverse, really. I mean, realistically. Because the capacity to convert the motion from, you know, a straight line pushed down, pushing something up won't give it velocity in a direction. But pushing something down, straight down, will take away the energy of something's motion in a direction.
Arrives. Well, let's consider two small metal bars, one hot and one cold.
Oh dear, this might be very boring. Let's see, should I play it or not? Well, let's just do it.
For this simple model, we'll consider only 8 atoms per bar.
Okay, so this is the simple part about the fact that the probability of being able to move heat from a cold thing, from a hot thing, to move heat from a cold thing to a hot thing, okay, from a warm thing to a hotter thing, and it's very improbable. Yes, but if you do it with this tiny number of possibilities, it's more likely that you can have something like that happen. But as soon as you have more than you know, 1 million atoms, the probability gets very low. So yeah, we can skip at this, because that's just basically understanding how permutations reduce aberrations. You know, so some results become almost impossible if you increase the number of permutations.
Completely solved. But I'm going to close my eyes and make some turns at random. If I keep doing this, it will get further and further from being solved.
Yeah, and there's a point where you're going to start making it more solved and less solved. So some turns are going to make it more solved, some turns are going to make it less solved. So that's not even true, that the more turns ensure that it's less solved. No. Some of your turns might be accidentally productive to solving it.
But how can I be confident that I'm really messing this cube up? Well, because there's only one way for it to be solved, a few ways for it to be almost solved, and quintillions of ways for it to be almost entirely random.
Right, I know, but you might have gotten to your peak randomness in the fourth turn, and now you're just going back and forth from a little more random to a little less random.
Without thought and effort, every turn moves the Rubik's Cube from a highly unlikely state, that of it being solved, to a more likely state.
So I don't know why this is part of entropy, to tell you the truth. This is a completely different subject, and it certainly doesn't show that there's no mechanisms that consolidate energy and that are opposite of entropy. So I don't know why they drag this in there, because it's just kind of bullshit. All right, back we are.
A total mess.
The best way to burn fat and get shredded is not keto.
Out and for things to get messier,
It's
then
not.
how is it possible to have something like air conditioning, where the cold interior of a house gets cooler and the hot exterior gets hotter? Energy is going from cold to hot, decreasing the entropy of the house. Well, this decrease in entropy is only possible by increasing the entropy a greater amount somewhere else. In this case, at a power plant, the concentrated chemical energy in coal is being released, heating up the power plant and its environment.
All right, so now he's going to talk about all the waste that he didn't have in his ideal engine. So the fact that we can't do this ideal thing, or sometimes anything close to ideal, because we have to deal with side effects, as a practical matter. And as a practical matter, this is all good energy. It's just not in a place we can do anything with it, and it costs too much to do something with it. So we could do it. We could capture all of the crap that comes out of the plant and use it, but it would just take too much. We'd have to spend money to build that efficient plant, and the extra money might not return us enough value because we don't care about the pollution. Pretty much. And we have to pay for it, right? We have to pay for doing it clean. And we don't want to pay for it.
Spreading to the turbine, the electric generators, heating the wires all the way to the house, and producing waste heat in the fans and compressor. Whatever decrease...
So waste heat just means it's inefficient. It's for us to capture it and use it. That's all it means. It doesn't mean it has to be waste. It's our choice that it's waste, because it's really easy to just cut a hole in your boat, okay, and poo into the ocean, okay? It's really easy to do that. So people do it. Because it's easy. Not because it's, it was impossible to do it any other way. No, we could do it another way. We chose not to do it the another way because it's too fucking expensive.
An entropy is achieved at the house is more than paid for by an increase in entropy required to make that happen.
So that's the part that's not true, okay? I just say it's not true that it has to be that way. All right. We can be more efficient. It's that we choose not to be.
But if total entropy is constantly increasing...
It's not. So again, it's not. It's constantly... I would argue the universe could, just from what we observe, we'd say, damn, it looks like it's pretty clumpy. So therefore, it seems like it's clumping more than it's... I mean, there's less supernovas than there are star clusters being created.
And anything we do only accelerates that increase, then how is there any structure left on Earth? How are there hot parts separate from cold parts? How does life exist? Well,
so I guess he's going to use the sun as one of the arguments, but there can be other arguments about the fact that depending on, they kind of argue that even Jupiter's moons, you go deeper, it gets warmer.
If the Earth were a closed system, the energy would spread out completely, meaning all life would cease, everything would decay, and
So obviously a closed system with no gravity, so everything would just fly off into space. We just have to blow on it and it'll fly apart. Well, I mean, rocks aren't going to fall apart, but you have to break all the atomic bonds to make all that happen. But I just mean it would be very easy to break it into chunks anyway.
mix, and eventually reach the same temperature. But luckily, Earth is not a
Luckily, whatever.
closed system.
So we can have a bunch of organisms slaughtered every day in a brutal, horrible way, because that's all part of the fun of being an Earthling. We accept all kinds of waste. That's one of the wastes we accept.
Because we have the sun.
So we have an atmosphere. The sun isn't all that. Okay? It really isn't. Okay? The atmosphere is the thing that makes life really possible, because it changes what that thing can do to you.
What the sun really gives us is a steady stream of low entropy. That is concentrated, bundled up energy.
The energy that we get from the sun is more useful than the energy we give back. It's more
So I don't know if that's even true, right? I mean, the sun produces a lot of visible light. Doesn't produce a ton of infrared or anything else. So I don't know where he got this from. I mean, the fact is that, yes, the stuff we're excreting is lower frequencies, okay, than the stuff that came in, but it's not that big a difference.
more compact, it's more clumped together.
Plants capture this energy and use it to grow and create sugars. Then animals eat plants and use that energy to maintain their bodies and move around. Bigger animals get their energy by eating smaller animals, and so on. And each step of the way, the energy becomes more spread out.
Okay.
So I don't even, it just doesn't make much sense that it's each step of the way. Because some of those steps, it's not spreading out, it's consolidating. Some of the steps are making oil. Some of the steps are making geysers. Well, that's not a step from the sun, so wrong. But I'm just saying, this it's not all one way. It's also still doing the compressing thing.
Oh wow, I did not know that.
There you go.
Ultimately, all the energy that reaches Earth from the sun is converted into thermal energy, and then it's radiated back into space.
Whatever thermal energy is, right? So even that's a really messy thing to say. There's no atmosphere in space. I can't jiggle the space's atoms. So thermal energy implies that I could just, allow the jiggling atoms on Earth to jiggle atoms in space, and it can't happen that way. So obviously it's all, the only way it can radiate the heat is to radiate it as electromagnetic radiation. It has to be a photon of some kind. There's no other way for it to radiate the energy except to shoot out a few atoms. Maybe a few hydrogens and heliums fly away with some momentum, and that takes away a little bit of the energy. But I'm just saying, realistically, right, it's not thermal. It's radiant. So he should have said radiant energy.
But in fact, it's the same amount. I know this is
You do know this is.
I'm a PhD physicist.
Oh, okay.
Ah, see, and you think there's something called 1/2 mv squared that has something to do with reality. You think it takes 25 times the fuel to spin a wheel 5 times as fast. Gotta wonder.
Okay,
anyway,
I trust you.
I trust you.
The increase in
Mistake.
entropy
See, look at the little squiggly line, I just, as soon as they drew that on the board, with the other line squiggling on top of it, I was like, No, 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 no. I can't do that, and I'm really complicated. I have a lot of tools, and I can do stuff, but I can't do that. How the hell does some elemental piece of crap? How can it do that dance? It ain't doing that dance. Photon don't do that. Don't play that. Photon don't play that.
Can be seen in the relative number of photons arriving at and leaving the Earth. For each photon received from the sun, 20 photons are emitted.
Okay, I don't know who's the authority for this calculation. Who says so? Who did the measurement?
Everything that happens on Earth, plants growing, trees falling, herds stampeding, hurricanes and tornadoes, people eating, sleeping, and breathing.
So it's kind of obvious, though, that some of this stuff, like I said, obviously we've added some old solar energy. So we've heated the Earth, okay, by pumping a bunch of combustibles and really, making them more entropied, okay? So they were low entropy in the ground. We put them into a high entropy state in this environment, and so we have taken stored solar energy. So it's not just the sunlight we get now, it's the sunlight 200 million years ago is being allowed to heat us some more.
Breathing, all of it happens in the process of converting fewer higher energy photons into 20 times as many lower energy photons.
Okay, so again, it says them, okay, but it's fine. I mean, the number's got to be some number. There's obviously, we're not going to radiate infrared, ultraviolet. So it's more likely to convert ultraviolet into infrared than it is to convert infrared into ultraviolet. So obviously this cycle would have some tendency, okay, to change these frequencies.
Without a source of concentrated energy and a way to discard the spread out energy, life on Earth would not be possible.
Whatever that, what part wouldn't be possible? So again, it's just, showing a jellyfish, there wouldn't be an ocean deep enough, or again, there wouldn't be a place, part of the part of the real geological record, or whatever you want to call it, biological record, is these vents, under the ocean, and there's a realistic possibility that life started there, where it wasn't about sunlight, it was about the heat from the Earth's crust.
It has even been suggested that life itself may be a consequence of the second law of thermodynamics.
So that's just more baby talk, so throw some woo on top of the woo.
Universe tends toward maximum entropy, then life offers a way to accelerate that natural tendency. Because life is spectacularly good at converting low entropy into high entropy.
So I guess, see, again, it's showing ants, and what are the ants doing? They're taking the energy and putting it back into some form that's some nectar or some other kind of juice they're going to make that's going to be very low entropy. High energy concentrations. So they're taking something that's very diverse and spread out, and they're going to take that leaf and they're going to turn it into something high energy, high concentrations. Our own body stores fat. These are just these blanket statements that all we do is take concentrated energy and make shit out of it. No, we do other things.
For example, the surface layer of seawater produces between 30 to 680% more entropy when cyanobacteria and other organic matter is present than when it's not.
So I don't even know what that means. It absorbs more heat is what I think he's saying. So it takes the sunlight and doesn't reflect it, and instead absorbs it and, heats the water, I guess is what he's saying. I don't know how it could really be entropic if it isn't creating heat, by their definition.
Jeremy England takes this one step further. He's proposed that if there is a constant stream of clumped up energy, this could favor structures that dissipate that energy. And over time, this results in better and better energy dissipators, eventually resulting in life.
Oh, I mean, it's just, there's so many ways you could argue that obviously what makes life is a DNA molecule, having a piece of chemistry that can replicate. And until you have that, obviously evolution is going to favor organisms that can get more activity out of the environment. That is, they can eat more stuff, move more stuff, do more stuff. Doing stuff is really good for your survival. So obviously it makes stuff that can do stuff. So obviously it needs to be able to absorb energy. It needs to find it in concentrations. It can't sit there and pick up little tiny. That's more work to pick it up, right? If I have to burn more energy to pick up the food and eat it, then I'm going to really be in trouble. I mean, there's little birds that do this shit, and you just say, how can they win? Because what they're picking is little crap up that you can't even see, and you're saying, how do they win? It seems like more work to bend over and pick the damn thing up than you could possibly get from it. But yes, obviously living things have to figure out that margin. They have to be above that margin. They have to do less work and steal more. But, they always go too far.
Or, in his own words, you start with a random clump of atoms, and if you shine light on it for long enough...
Oh, brother. You get a replicating molecule that can zip itself up and, cut itself in half. I mean, that's the real trick to it, right? Because having a DNA molecule ain't going to do you any good unless you got the thing to unzip it. If you don't have the unzipper, you got nothing.
It should not be so surprising that you get a plant.
Oh,
So
brother.
life on Earth
I mean, it really is a religion. It really just is. They just have turned it into such mush. Ugh, crap.
survives on the low entropy from the sun. But then, where did the sun get its low entropy? The answer is the universe.
No, the answer is gravity. Charge is really the answer, but the fact is the universe is full of force bouncing around, and the force ends up pushing everything into everything. You can't help doing it. There's no real choice.
If we know that the total entropy of the universe is increasing with time, then it was lower entropy yesterday, and even lower entropy the day before that, and so on all the way back to the Big Bang.
AT&T is uplifted.
So none of that's true either. Oh God, these commercials, this diversity thing. I mean, you can't relate to anything. I mean, even the commercials. I might as well be living in some other country.
So right after the Big Bang, that is when the entropy was lowest. This is known as the past hypothesis. It doesn't explain why the entropy was low, just that it must have been that way for the universe to unfold as it has. But the early universe was hot, dense, and almost completely uniform.
Yes, and again, who says so? So all this stuff, you're saying, well, yeah, let's say if you could make a neutron star that was gigantic, all the matter in the universe crammed into little tiny, all the electrons and protons smashed right next to each other, electron, proton, electron, proton, proton, electron, all just smashed together. You can imagine, though, that the charge pressure would be just intense. So, yeah, it would have to blow up eventually, right? Just because once it gets a certain amount of density, the interior pressures get insane, and all of a sudden, there's a point where you're putting, that any tiny movement out of place would end up cascading into a fracture or something. The balloon bursts. Yeah, it's not that complicated.
I mean, everything was mixed and the temperature was basically the same everywhere, varying by at most 0.001%. So how is this low entropy? Well, the thing we've left out is gravity. Gravity tends to clump matter together. So taking gravity into account, having matter all spread out like this would be an extremely unlikely state. And that is why it's low entropy.
So again, it just doesn't make any sense. Spread out is low entropy. So again, you get the point though. So he just mentions gravity as a side, like some little side thing, when it's the whole engine, okay, of the universe. The universe has no shape without gravity. If it's a bunch of little atoms that don't stick to each other, then nothing's going to happen, frankly. You know.
Over time, as the universe expanded and cooled, matter started to clump together in more dense regions. And in doing so, enormous amounts of potential energy were turned into kinetic energy.
So what does that even mean? I mean, potential energy was converted into kinetic energy. It's doing exactly the opposite. It's converting kinetic energy into potential energy. That's what a frickin' gravity's doing. Gravity is storing, it's a battery being charged. How can you call that potential releasing kinetic? No, it's exactly the opposite.
And this energy could also be used, like how water flowing downhill can power a turbine.
There you go. So there's an example of a force that's completely unentropic in the sense of it's concentrating energy. It's pushing it in one direction towards more pressure, and we're taking advantage of it. So it's not just about making energy spread. It's about just frankly taking it. You can take advantage of either cycle. The compression cycle, you can take advantage of it. The expansion cycle, you can take advantage of it. Both cycles are there to be abused. You know, we can stick our finger in them. We can stick our windmill in them. Both cycles are movement, and we can just steal movement. And that's all we steal. We steal movement.
But as bits of matter started hitting each other, some of their kinetic energy was converted into heat. So
again, more vague talk about blah blah blah. Heat is energy. Heat is momentum. Heat is whatever kinetic energy is. That's what heat is. Heat's movement. It's active energy. Oh, it's just so bad.
the amount of useful energy decreased, thereby increasing entropy. Over time, the useful energy was used. In doing so, stars, planets, galaxies, and life were formed, increasing entropy all along.
So it's just wrong. So again, we don't have to, there's no have to believe in a Big Bang. The whole damn universe could just be a static system and it works just fine. Get rid of dark energy, then you can get rid of dark matter, and then you just have gravity and explosions. Gravity and explosions. You don't need anything else.
The universe started with around 10 to the 88 Boltzmann
So they just makes this crap up. I mean, it's just disgusting. Ugh.
constants worth of entropy. Nowadays, all the stars in the observable universe have about 9.5 times 10 to the 80. The interstellar and intergalactic medium combined have almost 10 times more, but still only a fraction of the early universe.
So again, early universe means at some point in the expansion, and the expansion wasn't even consistent, so I don't even know what that even means. But clearly this is not even this is nothing like a rational thing to say. I mean, this isn't connected to anything called science. This is just fables and stories.
A lot more is contained in neutrinos and in photons.
Oh, yes, neutrinos. The things that have, like, zero energy.
Of the cosmic microwave background.
Just such crap.
1972, Jacob Bekenstein proposed another source of entropy. Black holes.
Oh, brother. So again, just too silly, right? It's exactly the opposite. I mean, the black hole is consolidating energy, and eventually you would argue that they must give it back somewhere. Hawking radiation is minuscule, so they're going to give it back somewhere. But I don't believe in black holes. I don't believe in singularities. I don't believe you can smash electrons into the same place in space. So all of that is just, in my opinion, garbage, and this image is garbage, and this is just all part of the religion. Here's a picture of the Holy Ghost.
He suggested that the entropy of a black hole should be proportional to its surface area. So as a black hole grows, its entropy increases. Famous physicists...
So it's just kind of silly to say it's less concentrated the bigger it gets, when obviously it's more mass, so it's obviously more mass under higher and higher pressure, which means it must be less entropic. So again, what the hell are they talking about? And it just gets bigger and bigger, right? Until we figure out what happens to black holes, right? There's no solution to a black hole except, well, something has to break and the black hole has to leak all of its energy out, right? Because it's just absorbing momentum. Everything's crashing into it, nothing's crashing out of it. So you've got to figure it's got a ton of stuff it can give back. I mean, if you believe in energy conservation, right, there's no point. If you're going to say black holes can just keep being black holes forever and just keep sucking energy out of the universe, well, then talk about how black holes are going to steal all the energy.
Physicists thought the idea was nonsense, and for good reason. According to classical thermodynamics, if black holes have entropy, then they should also have a temperature. But if they have temperatures, they should emit radiation and not be black after all.
Get training for a new career.
Fuck.
At Universal Technical Institute, we help students develop the skills employer...
The person who set out to prove Bekenstein wrong was Stephen Hawking.
And again, how, did he really prove there's any such thing as Hawking radiation? How did he prove it? It's just bullshit.
But to his surprise, his results showed that black holes do emit radiation, now known as Hawking radiation.
Yeah, some kind of radiation that isn't really radiation. So, I mean, again, so they talk about energy conservation. They just keep making up these imaginary things. So what is Hawking radiation? Neutrinos? What is it? Nothing? Bent space? Is that what it is? Oh, it's bent space.
And they do have a temperature. The black hole at the center of the Milky Way has a temperature of about 100 trillionth of a Kelvin, emitting radiation that is far too weak to detect, so still pretty black. But Hawking confirmed that black holes have entropy, and Bekenstein...
Well, whatever. If it has a tiny amount of entropy, it's the most unentropic thing in the universe. And it has entropy. It's bald, but there's one hair growing on its head. So therefore we'll call it Mr. Entropy, even though, we'll call him Harry, even though he always has one hair. Too silly.
Bekenstein was right. Hawking was able to refine Bekenstein's proposal and determine just how much entropy they have. The supermassive black hole at the center of the Milky Way has about 10 to the 91 Boltzmann constants of entropy. That is 1,000...
So again, it doesn't make any sense. It's spread out. It's the most concentrated thing you're saying in the universe, where the electrons and protons are in the same place in space. It's insanely, bizarrely tiny amount of space that it's in. It's about as unspread out as energy could possibly be. What the fuck? I mean, nobody can call bullshit on any of this bullshit. I mean, come on. It's bullshit.
Times as much as the early observable universe, and 10 times more than all the other particles combined. And that is just one black hole. All black holes together account for 3 times 10 to the 104 Boltzmann constants worth of entropy.
I don't even know how they're saying this. I don't even know what they're talking about. The entropy is the spreading out. That's what they say. More entropy means more spread out. Black holes are the most concentrated thing, theoretically, there could be. I mean, I'd say they're neutron stars, but regardless, a neutron star would be the most concentrated matter can be. That's the most concentrated form. The most concentrated form, and the energy is, the only reason why the stuff is concentrated is because there's enough pressure keeping it concentrated. And the pressure's been created by the energy that's trapped, pushing against each other.
So almost all the entropy of the universe is tied up in black holes. That means the early universe only had about 0.00000000000003% of the entropy it has now.
Oh, whatever. So I was just it's such jargon, and so I mean maybe he's saying that the black hole, he's actually agreeing that the black hole has an absence of energy, entropy, and therefore has stored entropy as non-entropy. But again, that's the problem with this word having only one use, one direction. We need a word for what it is when matter and energy is consolidated.
So the entropy was low, and everything that happens in the universe, like planetary systems forming, galaxies merging, asteroids crashing, stars dying, to life itself flourishing, all of that can happen because the entropy of the universe was low, and it has been increasing. And
so it's just silly. Okay, sorry. There's no reason to believe it's increasing. There's no reason to believe the universe is going to die a heat death or any of that kind of crap. There's no reason to believe because there just isn't enough evidence. So until you can demonstrate that, less energy is in the universe, that's, that we can visually notice that everything is getting colder, it's just talk.
it all happens only in one direction. We never see an asteroid uncrash or...
So again, the crashing of asteroids is the unentropy. They stick to each other. They clump and get bigger and bigger and hotter. Oh, brother.
A planetary system unmix into the cloud of dust and gas that made it up. There is a clear difference between going to the past and the future. And that difference...
Oh, so then to throw time in here is just such a pile of shit. There's no past and future. There's no such thing yet. There's just the present. The universe is working on it. It's heading for the future, and the past is just forget it. It's over. It's gone.
Comes from entropy. The fact that we are going from unlikely to more likely states is why there is an arrow of time.
Just complete bullshit. There's an arrow of time because stuff doesn't move instantaneously. And that's it. There's no other reason. If stuff could go from one place to another without having to take any time because it went instantaneously, then everything would happen instantaneously and there would be nothing happening. But the fact is, stuff is moving in a big void of space, and it has to move distances, and the distance it doesn't move very fast. So even though the speed of light is incredibly fast, it's incredibly slow also. It's really, really slow compared to instantaneous.
This is expected to continue until eventually
expected. This is all storytelling. So to throw this storytelling, this is just making shit up. Doesn't have really any reason for anybody to really believe any of this crap.
Energy gets spread out so completely that nothing interesting will ever happen again. This is the heat death of the universe. In the distant future, more than 10 to the 100 years from now, after the last...
So this is arguing that somehow the gravity has to go away. So somehow gravity has to end. Even for objects as they get further and further from each other, somehow the gravity has to go away. Because frankly, the gravity is always going to make something hot. Because it's always going to create a lot of pressure in the center. So frankly, anything could live in the universe forever as long as there's gravity.
Black hole has evaporated, the universe will be in its most probable state. Now, even on large scales, you would not be able to tell the difference between time moving forwards or backwards.
Oh, it's just it's almost evil that they would say something like that. Oh, time never goes backwards. Oh, god damn. It's just such bullshit.
The arrow of time itself would disappear.
Fuck you.
So it sounds like entropy is this awful thing that leads us inevitably towards the dullest outcome imaginable. But just because maximum entropy has low complexity does not mean that low entropy
So again, it doesn't happen unless you annihilate gravity, which you didn't explain how you're going to get rid of that.
has maximum complexity. It's actually more like this tea and milk. I mean, holding it like this is not very interesting. But as I pour the milk in, the two start to mix, and these beautiful patterns emerge. They arise in an instant, and before you know it, they're gone, back to being
Right, so pour oil into water, and oh, something completely different will happen. That's right, they'll mix, and then they'll separate completely. Oh, yeah, this is just such bullshit science. Watch me do it one way, but don't watch me do it any other way, right?
featureless. Both low and high entropy are low in complexity. It's in the middle where complex structures appear and thrive. And since that's where we find ourselves, let's make use of the low entropy we've got while we can.
Ugh, God, it's just such a religion. Oh, Jesus, I hate this planet. So that's worth 14 million views, and it's crap. It's crap physics, it's crap science, it's crap logic. They didn't test any of this crap, and they could have done simple demonstrations. They could have just said, pick up a magnifying glass and see the little spot I can make. Yeah, I've now done the opposite of entropy. I've taken something spread out and I put it and concentrated it. Fuck. It's not that hard to defeat the entropy. Alright. And again, I mean, to have to explain that there's gravity in this universe and it's obviously consolidating pressure. And pressure is heat. Alright, anyway, this is no point. It's potential heat, I guess you would argue in some respects, right? It's a tricky one. Because you can have a vibration that's so high that you can't, there's no way to detect that it's because it's too high a frequency. So you could argue that the push and pull, something can be vibrating so fast because it's in such high pressure. But that's the point, is that it's not heat as we know it because it's so hot. It's not useful. Can't do any work because it's so hot. You'd almost argue. All right. And it won't do anything until it's released, and all of a sudden it expands with a tremendous amount of stored pressure. All right. I mean, pressure should have been more of this subject, should have been the word pressure. Because pressure is the momentum. All right, anyway. Enough of the video. So, yeah, it's a little bit long. But damn. Very discouraging. So I'll watch some of these other videos. I've probably seen some of them, but yeah, you ought to, it ought to be pretty bad. I mean, a lot of them. All these references. So they actually watched all of these videos, stole the content essentially to make this piece of steaming crap. So anyway, until the next time and such.